All right, the 7.3 is in some sense is much simpler because it's still linear, but then linear with a constant coefficient. Okay, so all the coefficients are constant, and then because of this this simplicity, you can actually generalize it a little bit in the other direction. It can go to arbitrary order. So it's ODE with constant coefficient. Okay, let's click forward. So you write it in the form of 7.18 dy dx, the n derivative, and then a arbitrary coefficient, constant coefficient a minus 1 b n minus 1 y x n minus 1 all the way to the linear term. I mean, you have a first derivative, and then the constant terms multiplied by y. And the textbook equation has this inhomogeneous term, fx. But then it actually didn't present the solution for that one. Okay. Anyway, we'll talk a little bit about that later. So the solution is just by guessing. So for this constant coefficient, so one simple guess is just proportional to exponential function. Say the textbook at e to the mx. I mean, I don't like this notation. It's, m is not the integer, so when you write it, m usually just looks like it's an integer. M doesn't have to be an integer. Why don't we just change it? You can change it to something that more obvious is real, or even complex. Right, this is p, right? Then we'll see why is sometimes it can be complex right away, because we substitute this into here, the equation becomes obviously this is exponential function. All the derivatives just keep the exponential function, and then each derivative pull out a p, that becomes p to the n power, and then a n minus 1 p to the n minus 1 power. So you get a polynomial out, a1 p, and everything multiplied by the same y. That's just a sub 0. Multiplied by the same y. And we try to solve the homogeneous part first. The homogeneous solution is set the right-hand side to 0, and so that will give you opposed to the n solution, because you have a polynomial of n of all the n. So supposedly this one you can solve it, and just like formally it becomes p minus p1 minus p2. This is the fundamental theorem of algebra. P minus p n. Factorize that into here, right? So you have n solution p1, p sub 1 to p sub n, right? So the general homogeneous solution will be y, some kind of I from 1 to n c sub I. Y sub I will be e to the p sub I. That would be the general solution for the homogeneous one. So if you have the inhomogeneous part, you need to find a particular solution. Unfortunately, I've used the same p, but this is not this p, but this is just the usual label for a particular solution. So for a linear solution, usually it's like that. You found general solution for the homogeneous solution, and then which usually depends on arbitrary coefficient that need to be determined by initial condition or boundary condition, right? So all these C sub I, your n of that, because that's the order of the equation. But then if you have an inhomogeneous term, you need to find one particular solution that satisfies this solution with the right-hand side is with the F. So basically, you define this as the operator L. Basically, you require L of y sub p equals L. And all this L to the y sub I equals to 0. The y sub I is just the exponential function. Okay. That's the solution, right? It's okay. So that pretty straightforward, unless a special case if guys, here I'm just saying that there's all of them are exponential functions. Y sub i's are e to the p I. Just assume you have no degeneracy, which means all the roots are not the same. But then generally you can have the equations. It's like if pj equals to pj plus 1, right? Then obviously you cannot have two of them. If you have two you have e to the pjx and e to the pj plus 1x. They are the same, so they are linearly dependent. They're actually exactly the same. So you cannot use that for your general solution because you need n independent solution, right? Then what we can do is one of them choose like yj. It would be keep it like e to the pj x, and then yj plus 1 will be now using the same, because the p is the same, but then you multiply that x here. To make it linearly independent, then you see that this one still solve the differential equation, right? And then we will talk about how you check whether it's linear dependent, independent a little later in the chapter. But you see that they are the same. I mean, they both solve the ODE, but then they are linear independent. And the one mathematical way to get this form is to say that is pj plus 1 is not exactly pj, but the pj plus 1 is equals to pj plus epsilon, and then you let epsilon goes to 0. And so originally you can choose pj sub 1 because of this one, right? You can do that, but then when you take the epsilon go to 0, you take the difference between this one. Take the difference between pj and pj plus 1, or exponential function of pj x, and then the difference between that and the exponential function pj plus 1 or pj plus epsilon x. And then take the limit of that one, and you see that by doing a Taylor expansion, you recover that the linear order will give you this one, right? And so that's one way to look at why this is acceptable as a second solution for the same p. If you have a degeneracy, you have the p two values of index have the same p, then you use just multiply by x. And now you can generalize that. You have three of them, and one of them is just the original one, the other is x, and then the third one will be x squared, and then the fourth one will be x cubed, and so on. Just, you know the way to do it. All right, so that would be all the tricky part when treating this one. Otherwise, it's straightforward, at least for the homogeneous solution. It's okay. That's not much to tell. Now to come to the inhomogeneous one. So what to do with the inhomogeneous one? If you have inhomogeneous ones, the homogeneous one, you can get this part easily. Either the simple way like that, non-degenerate, or even with degeneracy, you know how to do it. But what about if you want to solve it with inhomogeneous term or the source term? What to do? How to find the y-sub-p? Or what are the full solution? How to do it? Any suggestion? Anyone has suggestion? Because add the terms. When you add all this, why I will not give you the right one, because the source term. Yeah, you have the source term, right? Then what to do? What do you get? Y or y-sub-p or y? The full solution. How do you get it? Just state what the general method you use. I'm asking you because you did that before. Because we changed the order of the course, different from the textbook. You did that before. I'm just reminding you what we did. What did we do to solve differential equation? Not separable as that one we have covered. We covered in the last semester one way to solve differential equation. Yeah, transform. What transform? Laplace transform. Right. You just Laplace transform because it's linear, and you know the derivative Laplace transform of the derivative. We talk about that. We get just like a p. You get the p, right? It's like a p n, and then you have a bunch of terms. The initial condition for the derivative, and then the function at initial condition of the function, and then you apply to all of them. So once you get that, the left-hand side will be a bunch of like right, a capital P of function P of the Laplace transform of y, and then there will be another term that depends on P, and maybe the initial ordered initial condition y0, y0 and so on, right? That would be the left-hand side. And the right-hand side, oh, this is a different L. Let's forget about this. This is the Laplace transform. And then the Laplace transform of L. Right? And then you solve for Laplace transform of y is just Laplace transform of f minus q divided by p. And y will be the inverse transform of that. Inverse. And you know the inverse transform, we talk about the inverse transform. You either look up the table or do the integral on the complex plane, right? Yeah, we'll talk about that. So Laplace transform F minus P minus Q divided by P. And if you use the integral, you're pretty sure that there will be contribution from the zero of this polynomial. And you see that this polynomial is exactly this one. Right, exactly this one. So all this, the root of the zero in this p in the denominator becomes the poles in the complex plane, and you do the integral. There will be contribution from this pole, which will give you the, because when you do the inverse transform, you multiply by the exponential function, right? So you recover all the exponential function pi, and then because of the contribution of the zero in the denominator, right? But then you have extra one, the extra singularity from possible singularity from the Laplace transform of the source term. That will give you, supposedly give you the inhomogeneous part. The one way to do it is using Laplace transform. It's okay. So, your textbook didn't talk about that. I mean, didn't have example for that, but yes, we did that in that chapter. At least some equation we did that, and then also there's another way to solve in homogeneous term. Your textbook has a later section in this chapter, a later section limited to the second order equation, but then it can be generalized to function the coefficient with x dependence that can be allowed also in that context, second order with an inhomogeneous term. And that method can be generalized in this problem also, except that I mean, when we went through that, you will see that all this the formula will involve this determinant of constructed by this function, and then also involving the source term. Also, there will be a bunch. If the order of the equation is large, you have the determinant, the rank of determinant will increase like a fourth order equation. Then you have determinant of 4x4 matrix. That I mean becomes a pretty the form is pretty complicated, but at least systematically you can develop that also. I mean, that is another method to solve for the inhomogeneous equation for this kind of problem. It's straightforward. I mean, or you can look up the formula from math textbook or math handbook. Okay, but anyway, your textbook didn't talk about it in homogeneous term, but getting in homogeneous term is not difficult, at least in principle. Okay.